Hi there. Welcome to GAAC. I just want to briefly say that next week's speaker, or next month's speaker, sorry, is our own Phil Orbanes, who always gives a very educational and interesting talk. So please come back for that. And we don't really have a what's up tonight, but as you all may have heard, that there's supposed to be an aurora display up tonight. So take a look after the meeting and see. It should be dark enough by then and see if we can see anything to the north. All right, tonight's speaker is Peixin Zhu, and she's a doctoral candidate at
The GAAC room is muted, Michael.
Oh. I have to do that later. I did it too early. Go ahead, sorry.
All right, and so please welcome Peixin Zhu.
Thank you.
Hi everyone. Thank you for asking me to give this talk. I'm currently, as just introduced by Michael, I'm a second-year grad student. I'm in Harvard University, working on a topic that is related to the radioactive activity in the galaxy center, which, if you have heard, is called for as AGNs. But if you haven't heard, then you can think about it as the actively accreting black holes as this event. So today I'm going to guide you through how astronomers study this kind of events and what we learn from these studies and what we can do better in this aspect. So the story starts when we obtain this beautiful galaxy image, which are not our own Milky Way because we are inside the Milky Way and we cannot see ourselves. But we can see through all the stars in our Milky Way and to the extragalactic. So these are the galaxies that are relatively nearby. So we can have a very good view of what is going on inside them, even with the like nowadays a bit not that exciting Hubble Space Telescope. So at that time when this image comes out for these galaxies, as you can see in this picture, that all these galaxies have well, they have all kind of structures, but the common part for these galaxies in this image is that they kind of has a disk where you can see, let me see. Okay. Well, I was trying to find my mouse, but I fell. It's okay. So as you can see in this image, these galaxies have disk, which is a slightly fainter outer regions. And then there's spiral arms, where is the bright blue parts in these spiral galaxies. And what you also can see is that they all have a bright center. So if your conclusions at looking at this image at the first sight is that all these galaxies have some activities in the center, then you have the right instinct. Other than that, we also want to learn more about the galaxies in terms of, instead of this comment, they also have some kind of different in the morphologies, right? For example, some sample, they have some sample, they have a merger shapes where it's not only one complete clean spiral disk you can see, but also like a kind of violent dispersion or turbulence structures. So for these galaxies, something special must happen to them. We want to learn better about what govern the galaxy evolutions, and that's the goals of all the astronomer that is working on the galaxies aspect. To study that, well, we spent decades of effort in studying these galaxies with all kind of informations, which I will introduce better later. But most recently, an exciting update in this field is that we finally have the GAAC telescope, which is basically a next generation of Hubble's, and showed us this beautiful, more detailed image about this nearby disk galaxy or spiral galaxies. So this image is released relatively recently. So it's kind of, as I remember, it's a couple months ago in these years. And what this image showing us is that with GAAC, first of all, this image looks apparently redder than the first one. The reason is because GAAC is observing in the infrared wavelengths. So it's red, as you can imagine, comparing to the optical image in the first slides. The second part is that you can see lots of filament structure and bubble structure, especially near the galaxy center. And that is what people think about today as the remnant of supernovas happening in these galaxies, which was not reviewed previously in the optical image, because in the optical, you basically see a very smooth brightness instead of in this image, which has a lot of structure. So GAAC is really giving us a new insight of what the morphology looks like in the galaxy inner center, in inner regions. Let's have a more direct comparisons of these two telescopes. So these two images, the left one and the right one, are for the same galaxies. NGC 1365 is a nearby spiral galaxies that is quite famous, and it's relatively face-ons. So as you can see that the spiral arms and galaxy center are quite obvious. And the direct comparison between these two images is that they are revealing a dusty structure, which in the left HST image show as the bronze area, and on the right show as the right area. And they somehow form a spiral arms shape structure that is extending toward the galaxy center, and where you can also see there's bright sources in the galaxy centers. So it means that from both these two images, you can see some structures in the galaxies. But what are these? What are the matters that are giving us such the information in the light? They are the visible things, or all the things you can see that is not dark. One is stars. So this, I point out the blue regions where the stars locate. But remember, they are not single stars. They are instead star clusters. Because they are extragalactic galaxies, you cannot resolve single star at that far distance. They are also gas. I point the gas to these bright red regions in the GAAC image. Basically because that's where these bright red emissions are coming from gas. But again, you cannot resolve gas, but you can know that these regions are abundant in gas. And they're also dust. So dust are those this filament structure that are relatively fainter, but are still apparently red in the GAAC image. So these are the regions that are dominated by gas, or at least the light we see in this infrared wavelength are coming from the emission from the lab, from the dust. And why does these emissions or lights coming from these three kind of visible matters? That's something that astronomers spend decades of effort to understand, and to learn from this light or brightness at certain wavelengths, to learn the structure and the parameters of the stars, gas, and dust. Basically, the visible matter of galaxies. But there's one more mixing part from this image is the dark matter. So we cannot see the dark matter through this image. We can only study them from the gravitational related evidence or something. So we cannot see them in this image. So basically from this image or the lights coming from the distant galaxies, all we can learn is the stars, gas, or dust. And as I mentioned, that all of the spiral galaxies we saw has a bright center. What are the centers could be? Like what could the centers be, and what could be the mechanism that contribute to this bright center? So here shows an example of what might happen in the galaxy centers. This image is a composite image combining the observations in optical wavelengths, radio wavelengths, and X-ray wavelengths, as shown on the right panel. So it shows you all the how this image looks like in certain wavelengths. So this is a quite broad range in the wavelengths. And by combining these three multi-wavelengths image into together, we can kind of review the structure of this galaxy NGC 5128. This is a nearby galaxy that is known to have a very dusty dust line that is penetrates across the galaxy center. One other thing is that you can see this giant lobe structure, double lobe structure in the radial wavelengths that is extending from the galaxy center toward the intergalactic scales. So the extended scale is comparable to this galaxy size. It means that something is coming out from the galaxy center. And what is coming out? When you look at the X-ray image, you can see there's a jet-like structure just by shooting from the galaxy center toward the outskirt, and the direction is overlap with the radial lobe. So this is the hint that something violent event is going on in the galaxy center. And through more detailed study, astronomers find out that this is an actively accreting black holes in the galaxy centers. So to be able to be visible in the X-ray and radio wavelengths, the black hole need to be actively accreting. By saying we have a parameter to characterize how actively they are accreting. We usually use an Eddington ratios. And in these galaxies, the Eddington ratio could be quite high, which is almost like comparable to 1. So Eddington ratio equals 1 means that this galaxy is accreting at the maximum limit that is allowed by the current theory. Usually for most of the more quiet black hole that was called like slowly accreting, or basically like non-accreted black hole, their Eddington ratio can be close to 0 and ranging from 10 to the -3 to 0. So just give you a broad idea of what the black hole accretion rate could be. So there are these actively accreting black holes exist in the galaxies. Another example is shown in this image is for the NGC 4261. Both these two galaxies are relatively nearby, and the common thing is that they all have a radial bright structure that is kind of a jet structure starting from the galaxy center, extending toward the outer part, and then the extended structure in the outer region are quite obvious. And these are the most common knowledge for the actively accreting black hole structure. And these phenomena are called AGN, Active Galactic Nuclei. So when we refer to AGNs, that this is the event or phenomenon that we are calling to. So let's come back to how does astronomers study galaxies? There are intrinsically two methods. On the left, showing you the photometry studies. Basically, you just use the whatever telescope in the certain wavelengths to take image of this of a certain area of this of the skies, and then you will get the image. Just show as the left part, the GWST's first light image. You can see that by just looking at the image, you can sort a lot of things. So one thing that is quite obvious in the GWST image is that you see some disturbed structures in the center regions. So you can see those we can see some lens galaxies around the galaxy centers, which they have some kind of symmetric shape and is not as we expected to be a rounded, extended shape. The other thing you can see is that if you look more detailedly, which astronomers do, the background, they contain a lot of little red dots. And when you zoom in to see the red dots, which is shown on the fourth right subfigures on the photometry panel, that's when you zoom in, you can actually see these are not really the dots. It's actually extended source in a certain shape. And by studying their spectrum, you'll be able to learn how far away they are. So the spectrum was shown in the right panel. Basically, you just use some spectroscopy to take the spectrum of these certain sources. And by studying the certain emission lines in this spectrum, as shown in the blue highlight emission lines and red highlight emission lines. So although these emission lines locate in the different observed wavelengths in these spectrums, but we do know that they are actually referring to the same emission lines in the vacuum wavelengths. So you just need to mark the observed wavelength to the vacuum wavelength, and then the difference in the wavelengths reflects the redshifts of these galaxies. And by studying the value of redshift, you'll be able to calculate the look-back time for these galaxies, or say when they are observed in this image. So as you can see that these four galaxies are actually, when we observe them, we are observe like from 11 billion years to 13 billion years old galaxies. So it's quite early universe. And this is how, although these figures represent how people learn the GWST data these days, for the past decades, that these are the methods that astronomers learned about all these galaxies, including the nearby galaxies and the a bit far away galaxies. So let me give more detailed introductions of how does astronomers study this spectrum. So before we look into how we can learn from this spectrum, I would like to introduce or talk about how this spectrum forms, how this astronomical spectrum form at the first sight. So this is a very simple toy model, as shown in the yellow circles over there. Let's assume there is a sources emitting black bodies radiations at the first. So a black body sources is kind of, you have a fixed temperature, and then all the spectrum shape emitted by the black body sources is just as predicted by the black body radiations formulas. So it's a quite smooth structures in the bottom left. But then on the way that these black bodies radiation reach us, there are a clump of diffuse gas. Where are these diffuse gas lines in the universe? It could be the outer layers of the stars, or we call the stellar atmosphere. Sometimes it could also be just a nebulars, distributing in the galaxies. So whatever these diffuse gas are, as long as there are diffuse gas on our line of sight, we will get some additional structure from in addition to this black body smooth spectrum. So if you're looking through this diffuse gas, most of the time you will get absorption lines, as shown on the top right. This absorption line is based on the black body spectrum, but you get the depletions or absorption in some certain wavelengths. And by interpreting these wavelengths, you can understand what's the composition of this diffuse gas, and sometimes also like what's the density of this diffuse gas, and what's the ionization state. For example, how many atoms are ionized to which level, etc. thing. And if you're looking at us from the side of this diffuse gas, because you're not directly looking through the diffuse gas to these black body radiation sources, then you don't have this background black body spectrum. Instead, you have a very basic flat spectrum. But in addition to that, you also have a couple emission lines, as shown in the bottom right figures, that at some certain wavelengths, you have excess of the fluxes in that wavelength. So this emission line can also tell you about the properties of this diffuse gas. It can tell you the density and also the compositions. Somehow in astronomy, people call it mentalistic. Mentalistic is basically the idea of compositions. But in addition to that, we also care about like how much, what's the fractions of non-hydrogen atoms comparing to hydrogen atoms. That reflects star formations, how many generations of star formation have happened. So the composition of the mentalistic is an important parameter for us to understand the diffuse gas in the extragalactic galaxies. And we can also learn about, for example, the same one, the density and the ionization state, like how many atoms are ionized for each element. This sounds kind of boring, is it? But that's the work of most of the astronomers if they are studying the spectrums of this galaxies event. Okay, so as I just mentioned, this is a rather simple model because we assume that the source is a black body source. But most of the case, like objects are not perfect black body. For example, I think the object that is closest in the astronomy that is closest to black body is stars. So for stars, you can usually just assume a black body spectrum as the continuum, because spectrum for stars, they usually have a constant temperature in the photometry. So that they have a very constant temperature outshell shells, and then emit this continuum. But in addition to this black body continuum, you can also observe some apparently absorption lines. So by learning how deep these absorption lines are, and then at what wavelengths they're happening, and how broad these absorption lines are, they can study the stellar atmosphere, as I mentioned. And based on the continuum structure, you can also learn the temperature of this of these stars. And based on what absorption lines you observe, for example, what elements contribute this absorption line? For example, in this spectrum, if you can see it clear, then you probably can see there's nitrogen absorption lines, oxygen absorption lines, meaning that at the outer shell of these stars, you do have oxygens and nitrogens elements instead of only having hydrogens. It indicates the phase the stars are. But that's not the main topic of our talk today. There's also a kind of spectrum you can observe. It's a nebular spectrum. As I said before, if you are not directly looking through the diffuse gas to sources, then you have a very flat continuum as shown in this nebular spectrum. But you do observe the emission lines in this case. So this emission lines tells you the abundance or the metallicity of the diffuse gas that compose this nebula. So by studying this spectrum, people can understand what the composition of this nebula are. These are not galaxy spectrum. I used to have a very naive question when I just started learning astronomy in my undergrad. I asked my teachers how they distinguish the stars from galaxies, since they are both, well, stars is a point source, right? But if galaxies are far away enough, then they are also seems like a point source. So it sounds to me that it's very hard to distinguish from the point source that whether it's a distant galaxies or just a star, nearby stars. It turns out that the solution is from the spectrum. So these are the spectrum of the most typical galaxies. On the left, I'm showing the spectrum of the galaxies, but dividing into different morphology shapes. So this, the morphology shapes E4, SA, SB, SC are the Hubble sequence, which just classify based on how rounded they are or how spiral they are, whether how many spiral arms do they have, or is there a bar inside or something. As you can see that the top panel and the bottom panel, the spectrum look quite different. But comparing the left panel to the right panel, there's not much that difference in this galaxy spectrum. It basically told you that galaxy morphology is not the main cause for the difference in this galaxy spectrum. So when you saw these distinct shapes in the galaxy spectrum, you're actually seeing something more fundamentally governing this difference. That's what astronomers want to learn. What is causing this difference? And let's recall it what the stellar spectrum looks like. It has a black body continuum plus the absorption field, plus some absorption lines, right? We cannot see any, we cannot see a very clear shape of black body emissions on the top panel. So it indicates that this is apparently not a single stars. And we cannot also see that black body spectrum in the bottom panels. So also told you that it's not a single stars. That's what distinguishes galaxies from the stars. But somehow you can think that the bottom parts are a bit comparable to a nebula. Yes, it has two bright emissions as what the nebulous spectrum looks like in the previous slide, but it also have additional other emission lines in this spectrum and plus some absorptions. So in this case, that's how you identify this is actually a galaxy spectrum, which is the combination of thousands or millions of stars, stellar spectrum, and like some nebulous spectrum. So that's how they look like in the current shape. Then what is really governing this, the shape of the galaxy spectrum? After studies for decades, people finally figure out there is a certain mechanisms hidden or telling us from there's a hidden mechanism that's happening in this galaxy center that this spectrum told us. It's basically whether they host actively accreting black holes or AGNs. So here is a diagram that is showing 8 different galaxies based on their classifications of, for example, what kind of AGN they host. So in the bottom left, normal galaxies, which means that there's no signs of observable AGN's activity in these galaxies. So you can see that the continuum has some shape and plus some absorption lines, and basically no apparent emission lines in these galaxies. So if you find a galaxy has a spectrum like this, then it means that it's not a active galaxies based on the current astronomy classifications. Then all the other 7 panels are somehow are AGNs in some certain criteria. So they can differ in the orientations, depending on what's our field of sight angle, respect to the AGN's symmetric axis angles. Something like that, and also different in how bright the AGN are, or how violent the AGN activity are, or on the other word, how actively the black hole is accreting. That will result in different emission lines in different spectrum as we observe. And besides of just classify them, we do want to learn better. Is there, does all this emission line indicate the presence of an AGN or actively accreting black holes? Could it be coming from something else? Unfortunately, yes. This is a work that was done in 2006, so it was almost 20 years ago, where people studied the most prominent emission lines from the galaxy spectrum. So on top left, I'm showing an example of galaxy spectrum. Here you can see the brightest emission lines are marked out, including the hydrogen H alpha, H beta. These are hydrogen lines. By seeing these lines, it means that it has a bunch of hydrogens, ionized hydrogens in the gas. You can also see there's a bright hydrogen 2 emission lines coming out next to the H alpha, right next to it. And this is indicated there's ionized nitrogen atoms in this gas. There are also bright oxygen lines. There's oxygen 1, oxygen 2, oxygen 3, indicating the different ionization states of the atoms, basically meaning that whether they lose 1 electron, 2 electron, or just saying that neutrals. So it means that for this gas, from this gas or the gas in these galaxies, they have relatively abundant elements of oxygen, nitrogen, and sulfur. And by studying, and astronomers have found that by using the H alpha emission line flux, H beta emission line flux, O3 emission line flux, and nitrogen 2 emission line flux. By using these 4 emission line flux and using their ratios and plot onto a 2D diagrams, they found that somehow they can classify these galaxies into 3 categories. One is H2, or more blankly, the star-forming galaxies. These galaxies, although they have a bright sources in the galaxy center, as shown in the NGC 5238 image, they do have a bright center in the optical image. But these bright centers are actually contributed by a starburst event or star formation event instead of actively accreting black holes. So these are not black holes accretion events. These are pure star formation galaxies. And the reason that we are still seeing so much emission lines is because the star formation is so violent that it generates rather hard radiation fields, which can ionize the nearby gas and ionize the atoms in them to the certain ionization state and emit all these emission light that we observe. There are also a category of galaxies that are classified as Seyfert. So Seyfert is actually the named Seyfert is actually an astronomer's name. That Seyfert, the person, published a paper in 1943, summarizing or publishing populations of point sources that, although they look like stars, they are point sources, but they have very distinct spectrums that are totally different from the common stars spectrums. But at that time, when Seyfert published this population, it was not well recognized for sadly 60 years. It was after it was 16 years after when people really look into this group of populations and realize that that's the first ever detections of this actively accreting black hole galaxies ever since the study of astronomy. Okay, and there's also one other group called LINER. That the origins of LINER's galaxies are still unclear, so people are still debating on what is causing LINERs. But let's just keep in mind there's one other kind of galaxies that are not belong to either star-forming galaxies or Seyfert galaxies. And all these studies are based on these 4 emission lines and their line ratios. And all the gray dots I show in the bottom left figures are actually representing one galaxy. So as you can see, this is a very condensed distribution of gray dots. Gray dot means that this figure compile the observation of millions of galaxies in the nearby universe. And now we have known that there is such an for some galaxies or for like as you can see previously, there's a lot of gray dot in the Seyfert regions. So there's a large portion of galaxies that host actively accreting black holes. What can that tell us? There is in astronomy, there's another breakthrough in the early of 21st century, is that people realize that the black hole mass and the galaxy mass are somehow correlated. They form such a very tight correlation as shown in the lab figures, indicating that if you ever estimate the total stellar mass of the galaxies, you can estimate how big the black hole are, like what's the mass of the black hole in the center. It indicates that the growth of galaxy stellar mass, or for example, the star formations, the star formation rate should have somehow be related or correlated to how the rate that the black hole mass grows. But as I mentioned before, that black hole accretes material, it does not sound any process will link to the star formations events, right? So it was a mystery. Well, it's still kind of unclear, so I cannot say it was. It's still a mystery of what is governing these correlations of the black hole mass and the galaxy stellar mass, or like what is the link between the star formation of the galaxies and the black hole accretions. There is a recent study, this is performed in 2018 and published in Nature. They study that they divide all these observed galaxies into 3 populations based on their location of this on the figures on the left. So there is a group population marked as red that is a bit above these relations, the fit of these relations, the gray line. So this population, they call it overmassive black hole galaxies. It means that with the same stellar mass, they're having a bit heavier black holes than the other populations. It means that in their evolution history, there must be a case where their star formations, where their star formation rates was higher than previously, and so they form. The star formation rates was lower than previously, and then they form less stars at the same black hole mass. And there is another blue populations called undermassive black holes that people classify them as the at the certain galaxy stellar mass, they have lower black hole mass, indicate that in their galaxy evolution history, there must be a period where their star formation rates was higher than other populations. And that is what this group studied using their spectrum. And they figured out that this is actually the case, as shown on the right. So the look back time zero means current or the present. And look back time 10 gigayears means that you are looking back at 10 gigayears earlier and at the early phase of these galaxies. And you can see that the star formation actually, recently the star formation are as expected at roughly 0.2 gigayears. The undermassive population have a larger star formation rate than the average and then the overmassive populations. This is just a broad idea of how these distributions are formed, but there's even unclear questions of what exactly is linking the star formations of the host galaxies and the black hole groups. And that is what's still confusing astronomy these days. And people are spending lots of efforts in this field. And this is it's a very active research field these days in astronomy. Here I list 3 possible mechanisms that people, astronomers kind of have some consensus on how this correlation could happen. So these are basically contributed by the mechanism called agent feedback. And this feedback not only happens in one scale, but instead happening in multi-phase, like multiple scales. From the smallest scales on the top left, you can see that this is less than 1 parsec scale. So 1 parsec is basically just black hole and its in its vicinity, including the accretion disk. So in these small scales, black holes are accreting material from the accretion disk, and they also eject some turns of energies and radiations because they need to maintain momentum, equilibriums, etc. thing. This is governed by the current physics and current physics formulas. And then there is a larger scale at 1 parsec to 1 kiloparsecs. 1 kiloparsec is roughly referring to the scales that we observe the spectrums from this galaxy center. So remember the plot where I shows the galaxies and the center little white dot about where we extract the galaxy spectrum to study their either their H2 ciphers or liner. That is the scales of 1 kiloparsecs. Is the center regions of the galaxies that can be resolved. And at the larger scale is over 10 kiloparsecs. So 10 kiloparsec is a scale that is even beyond the galaxies, or from the galaxy center toward the galaxy edge. So at these scales, that the agent feedback is not only affecting the galaxy's medium, but also the surrounding material, including maybe nearby system, like nearby galaxy system, if they exist. So these are the main three mechanisms that we all classified as agent feedbacks that people propose to be the solution that maintaining this well correlation between black hole mass and galaxy stellar mass. But at what scale can we study the agent feedback these days? Well, we were always hoping to do like the best job, which is like to see the black holes, which recently did come true by the EHT collaborations. They are successfully take an image of the center black hole in the M87 and also our own black hole in the Milky Way. And this scale is like the scaling length is 0.01 parsecs. But does that mean we can always reach these resolutions all the time? Unfortunately, that's not the truth. It takes so much effort to reach these resolutions, and we were not able to afford it like more than a couple of times, I would say. So if you want to study a larger population, we need to compensate on this the resolution scales. So most frequently used physical scale that we can study is still in these B situations, which is typically ranging from 1 to 10 kiloparsecs. This is the most economic way that we can afford and still do a systematic surveys of a large number of galaxies. But instead of learning, as I mentioned before, like there are agent feedback that is not only within 1 kiloparsecs, but there are also a phase that is extending toward 10 kiloparsec or so. So if you want to learn these scales, these two scales, agent feedback, we need more information rather than just one single spectrum from the galaxy center. And that is what this new technique of spectroscopy coming in. So the idea is shown on the bottom in the top left figures. Instead of having only one single spectrum at the galaxy center, you have an extended, you have a 20 or 30 a group of spectrum carrying across these galaxies. The idea, how they achieve this is showing on the bottom left figures, where you just divided the galaxy image into different little boxes. And after the different, and behind all these boxes, you have one fibers. And then you combine all these fibers and then going through this spectroscopy and reach and obtained, going through the optical gradient and then obtained one spectrum for each of the fibers. That's how you get, for example, 20 or 30 spectrum for the single galaxies. And this technique has been well applied to the galaxy observation since 2015. Now we have already a bunch of, well, thousands, I would say 10,000 of galaxy observation with IFU spectrum. So with this, we can do some new studies. Remember that I mentioned the diagram that consists of 4 emission lines, and then the 2 axes are the emission line ratios. These are the same diagrams. But instead of obtaining only one data for one galaxies, now we can obtain hundreds of data for the same galaxies. How does it look like? Well, for this galaxy, particular galaxy that I show as an example, a GC 1068, it used to be only one dot lying in the Seyfert regions in this diagram. But now, as you can see, when now we have the spectrum that spread all over these galaxies, you can see all this data from a sequence that extending from the H2 regions, which is representing the star-forming galaxies regions, toward the Seyfert regions. So this shows us, this is a sign that in this galaxy, there is a mixing happening. there are some regions that are star formation dominates. And there are also some other regions that are AGN dominate, or like these regions are close to this actively accreting black hole. That's why they shows a spectrum that looks like the AGN dominates spectrum. And on the right, I'm showing how when we plot back all this spectrum back into the galaxy image, how does the distribution look like? So these are all having the color codes of this dot are showing their contributions of AGNs based on the single scale calculations. So on the right figures, you can see, so the right part of the right figure is just a zoom in. So they are actually the same figures. That in the galaxy center, there's a bright part, meaning that in the galaxy center, they are close to 100% contribution from AGNs. And then there's also two shell structures in the top and the bottom from the point sources, from the bright sources in the center. These are also have a good or great contribution from the AGN, roughly 80% or something. And then in all the other regions, which are shown in the purple and dark blue, they are mostly dominated by star formations. So now with this IFU spectrum, combining with our previous tool, we'll be able to study how this star formations activity and black hole accretion activity distribute in these galaxies and how they mix with each other. So by studying them, we could probably understand with more detailed follow-up studies, we'll be able to understand, does the actively accreting black hole affect the star formation rate in the nearby regions? And how does it relate to the AGN feedback in our understanding, and to understand how the black hole accretion co-evolve with the galaxies star formations. And recently there's well, the picture I told sounds perfect. But in practical, it was more complicated than we hope. That's always the case in science. The basic reason is that, as shown in the top right figures, even though you are still expecting star formations regions shown by the blue grid, AGN's region shown by the red grid are locating in that certain regions. After the theoretical calculations, you also expect two other kinds of excitations that can contribute to the similar spectrum that are identified as AGNs and star formations, which is represented by the purple grid and the black grid. And these are shocks. What are shocks? Well, as you can imagine, shocks reflects a violent event, which is not belongs to star formations and also not belong to black hole accretions, but instead it represents an activity that when a violent jet coming out from the galaxy center, and then they interact with the surrounding ISM, interstellar mediums, well, the surrounding mediums in the galaxies. At the interaction phase, this kind of shocks happens. So the shocks is an independent excitation sources that are independent from the AGNs and star forming regions, and yet can cause confusions in our studies. So there are new techniques to distinguish these shocks from this AGNs activity and the star forming activity, which is a new 3D diagram. So as shown on the left panel is showing these new 3D diagrams. These diagrams are based on the 2D diagram as shown in the bottom right, but combining with one more information of the velocity dispersions. The simple interpretation of velocity dispersion is just how broad the line is. So the width of the emission lines contains some kinematic information, and by extracting that kinematic information and put it in these three diagrams, we'll be able to disentangle shocks from the AGNs. And that is how the most up-to-date technique to study the IFU spectrum of these nearby galaxies that potentially contains this mixing. So the result of these new series diagrams is that we can now separate the contribution from star formation and shocks and AGNs, and recalculate what's the emission lines in certain emission line. For example, on the left, I'm showing that the H alpha emission coming from star formations, and course comparing with the CO carbon dioxide emissions that is in the radial wavelengths. And both these the CO emissions is coming from the cold gas, which is the arranging of star formations. So stars from the cold gas. Stars form from the cold gas. So the detection of CO emissions means that this region are likely or is the reach of CO emission indicates that this is the perfect environment for star formations. And it's always connect or related to the star formation event happening in these galaxies. And on the right, I'm also showing the O3 emission from the shocks, which showing you the shocks, how the shocks distribute in this galaxy center, and comparing with a radial continuum, which is reflecting the jet event that is associated with shocks. So these two figures is course comparing with each other, and you can see that they have very similar shapes in the similar regions, meaning that these separations results are performing rather good. And then other good things about these studies is that it is indeed very expensive to obtain multi-wavelength observations on the same galaxies, because as I said, we have millions of galaxies in the universe, and it's for each galaxies or each observation, it takes you, well, for each night, if you want to buy one night for you to observe an object, it could cost, as I remember, it's like $10 million per night. So it could be very expensive to require that all galaxies has multi-wavelength observations. But now if we have, as we have this technique to separate the agent activity or black hole accretion activity from the other two activity, that will be able to study this black hole accretion event only, even though we only have optical observations, which are the most abundant observation these days, and is more reachable and obtainable than the observation in the other wavelengths. So it is really helping us in our next steps studies of to understand these AGN feedback mechanisms and these black hole accretion events. And I think that will be the main part of my talk. Thank you, everyone. Do you have any questions?
Peixin, how much more telescope time do you need to rent to get one of these multi-spectrum images?
Yeah, so basically because these are nearby galaxies, so the time they need are relatively like lower than the the more distant galaxies. And for example, for these galaxies, which is rather nearby, that if you want to obtain, for example, the CO image, that will cost you a couple hours. And then this one also a couple hours, like roughly 3 hours, I think is enough for this one. Yeah, but think about how many nights do you have, or how many clean nights do you have per year, and how many hours do you have per night, and that's how it like how much it costs to get the information for one galaxy.
Okay, thanks. I have one other really quick question from the beginning of your presentation. There was a galaxy that you used, I think it was like 5128, or it was a number, it was in the 5,000s.
Yeah.
You had the radio spectrum with the lobes, that one. It's like two galaxies together. It looks like an elliptical has swallowed up a spiral. Is that the case with that dust lane?
That's a dust lane. It's not spiral. These galaxies are relatively edge-on.
Okay, so that's...
You're right.
Okay, thank you.
So Peixin, I have a question.
Yeah.
Which goes back to your first spectral image of NGC 1068.
Okay, yeah.
So if you could find that.
This one?
Yes. And so what I see in the right-hand panel is emission coded according to the key on the bottom left hand, right? So what I'm seeing is some spiral arms surrounding the nucleus that have indications of high oxygen 3 and high nitrogen 2.
Yeah,
Okay.
exactly.
And so those spiral arms, and you zoom in on it, and you can sort of see at the edges of the other one that they yes, indeed, they have this high excitation. And are you attributing that to the shocks?
Yes, that is actually why I mentioned that there could be contamination from shocks in this event. Because it's off nucleus, like it's not in the galaxy center, this bright arc structure. So they're actually not likely to be AGNs. So they are the contaminations of like shocks in our like this in the identification of AGN in this slice. That's why we need a better technique to improve these separations, because we need to account for the contamination from shocks.
So are you attributing these shocks in these what look like spiral arms, inner spiral arms, to the effects of a jet that is traveling through the plane of the galaxy?
That's a very good question. That is like a likely explanation for this case, but to obtain the more like a better understand of this case, we do need multi-wavelength observations, which unfortunately this region was not covered, like fully covered in our current observations. So if you want to identify whether it's a shocks event, or is there other things that is contributing to these regions, we do need follow-up observations in for the shocks event. We do need observation in the X-rays and the radioed follow-up.
Thank you.
Yeah, thank you for bringing up this question. This is that is how astronomers find out new things from the data.
Yeah, great.
Any other questions in the room? What about online?
Crickets.
I think you just bowled everyone over, as we say. Thanks for showing us how the sausage is made.
Yeah, really.
Thank you.
All right, Peixin, if you will email me your address, I'll send you a T-shirt. Send me a size, and you'll get you'll be the envy of everyone in Cambridge.
Thank you, everyone. Yeah, I will definitely do that. Yeah, thank you.
Thank you very
Have a
much.
good night, everyone. Bye.
Thank you.
Well, folks, that's GAAC.
That's it, that's it.
Wow. Okay.
Go see if you can see the northern lights and let me know.
Check, it's still too early.
no.
Still too early, we still have a lot of.
So.
Guide well out there right now, it's a little too early to worry about. Orange yet, don't have too much about.
Enjoy your
Okay,
cookies,
folks, we're gonna
everybody.
shut the doors. Thanks for coming, everybody.
Thank you.
Connie, Arthur, everybody.
Have a good night.
Thank you, Michael.
Because there's still.